Okay, so in section 5-2, we're going to be looking at polynomials and their linear factors and how they're connected to their zeros and how we can use that to help us with graphing. So definitely the main objective here is we're going to be looking at these polynomials that we kind of covered in 5-1. We talked about their degree, number of terms, first names, last names, things like that. And now we're going to start to transition into zeros and how zeros can be used for two different purposes. We can use zeros to help us for graphing functions. We can also use zeros eventually later on in this unit, in Unit 5, when it comes to finding solutions, much like with quadratics in Unit 4, where you were able to solve and find the solutions for x eventually. And later on in Chapter 5, we're going to be looking at how we find the solutions for x when we're looking at third-degree polynomials and fourth-degree polynomials. And something down the road that's coming that's very, very important, the fundamental theorem of algebra, to help us come up with all of those here. But first, let's just worry about factoring, okay? So let's look at problem number 1. Problem number 1, what's the factored form of x cubed minus 2x squared minus 15x? So first of all, notice that there are no no equal signs here. So all we have to do is to simply look for factoring. And this is one of those big three. Factoring that all Algebra 2 students need to know how to do, and that's be able to do GCF. So what you notice here with x to the third, negative 2x squared, and negative 15x is that they have a common factor, and all that is just x. So we are going to factor out that x, and that x gets factored just like this, and pretty much what we can turn that over to is division. Hey, I think in your algebra classes, you remember this little rule when it comes to exponents. If I had x to, say, the m power divided by x, the same base, to the m power, remember this little move right here? You just simply subtract the exponents. That's kind of what we're doing right here. Think of x as being x to the first. So if I were to take x to the third and divide that by x to the second, 3 minus, I'm sorry, not x to the second, but x to the first, it's like taking a 3 minus a 1. That's why we see x squared right there. Repeat this process. Negative 2, x squared divided by x to the first. That's why we have negative 2x. And then negative 15 divided by x. X is divided out to be 1. You're left with negative 15 times 1. So that's why we have negative 15 right there. Hey, don't think you're off the hook, because then, once again, you factoring experts from Chapter 4, you need to know how to handle that guy right there too. And see how we can factor that just like that. Two numbers whose product is negative 15, their sum is negative 2. Would be a negative 5 and a positive 3. And away we go. A lot of people forget to copy down that x that you factored out just a couple minutes ago. Okay? And also, there is no reason why you can't check that at work. So make sure you're checking your answers. Okay? So right over here. More practice. Okay? Do two things. If you're watching this video in class, go ahead and pause it, teacher, and go ahead and give the students a chance to factor this. So picking it up right here, not finished yet, but I just want to make sure we're all on the same page here. GCF should have been x. So when you factor that x out, what's left inside the parentheses will be x squared minus x minus 12. And now, let's look to see if we can factor the expression inside the parentheses. Can we come up with two numbers whose product is negative 12 and their sum is negative 1? Where am I getting the negative 1 from? Yep, right there. Okay? I think we can do it. X times x to give us the x squared. 12, I think a 4 and a 3 would probably be what we need here, because they have a difference between them of 1. So to pick up a negative 1, I think we need to lose 4 and then jump ahead 3 to put us at negative 1. I think we got it. Okay? This is us checking our work. I'll check it here in green by foiling first, outer, inner, last on that guy right there. So then I would have here x squared, outer 3x, inner negative 4x, last negative 12, x times x squared, like terms, that would be minus 1x, and then minus 12. So far so good, because you see right here, match here as we have up there, and then distributive property, distribute, 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 and I believe we do get this back up here. Okay? And so, when we talked about that objective about polynomials and their linear factors, polynomials are going to have linear factors, and those linear factors are what we're getting right here. Linear is just a big fancy word for any x that's being raised to the first power. So right there we have three linear factors. We have x, x minus 4, and x plus 3. Those three linear factors multiply together to give us this cubic polynomial here. Okay? So a couple of truths that happen with polynomial functions is that we do get linear factors of those polynomials. Okay? And then if we have a linear factor, say for example an x minus a b, what that tells us is that b would be a zero of that equivalent function, which would also make it a root. And I'll talk more about that here in a second. And b would be an x-intercept. All these basically, if I highlight these three right here, all three of these honestly are saying the exact same thing. The reason why these math textbooks have to put all three of those bullets down is because we have different definitions, different vocab words we use when we're using a function versus an equation versus a graph. Okay? And so when we are looking at a graph of a polynomial function, we call these three guys right here, here, and here, we call those zeros. Okay? We don't call them roots. We call them zeros. If we were solving an equation, we would call them roots. Don't ask me why. It's different, but just realize that if you hear those vocab words thrown at you, roots, in all intents and purposes mean the same things as zeros. Okay? Does it make sense why we call them zeros? Because at those three spots, that's when the y is 0. Okay? So what are the zeros of this function right here? Since it's already written in terms of its linear factors, the zeros would be when we take each one of these three linear factors and set them equal to 0, like you see right here. X plus 2 could be 0. X minus 1 could be 0. Or x minus 3 could be 0. And so then when we solve each one of those with a one-step algebra problem, in other words, subtract 2 from both sides, add 1 to both sides, add 3 to both sides, we end up with those three zeros right there. Okay? Now, when the question asks us to graph the function, as it's asking us to do right there, here's the only thing I need you guys to do. It's pretty straightforward. When you make a graph of that function, here's all I want you to do. That's it. So don't overthink this, please. Don't overthink it. First, get those zeros just like we got them right up there. Pretty easy game, that opposite game you guys have been playing since quadratics in chapter 4. Okay? Plot those three zeros there. Do you notice that you have a leftmost zero, which is this guy right here, and you have a rightmost zero? Okay? You have one at -2 and you have one at 3. Let me use more highlighting here. When we're talking about step 2, find all of the x values between the zeros, all I need you to do is give me all of the points that would exist in between that leftmost zero and that rightmost zero. The reason why we don't need to worry about anything else after that, outside of that green rectangle I just put there in the graph, is because of that concept we talked about in 5.1 about end behavior. Think about it for a second. X times x times x. So eventually this polynomial function is going to have a leading term of x to the third. And since that's a 1 and a 1 and a 1, we're going to have 1x to the third. So isn't that a positive number? And isn't the degree odd? So shouldn't the right arrow go up and the left arrow go down forever after we get past those zeros? That's why we don't worry about those. And that's why I don't let you worry about those. So, backing it up here a minute. When I'm asking you to just plot the x values between the zeros, certainly try that graph in calculator, as you can see with that screenshot I have right here. And then look at the table. You can see that all you need to graph for me are these guys right here. And notice that some of them are even graphed already for you. The one with the zeros, once again, that's why we call them zeros, is that these guys here, here, and here have already been graphed. All we need to graph is -1, comma 8, doot, that guy right there, 0, 6, doot, and 2, -4. That right there. Okay? You plot those, you're good to go. Okay? So let's look at the other problem here. What are the zeros of x times x minus 3 times x plus 5? Remember, you don't need to use the graphing calculator to find these zeros. They're actually staring you right in the face. Okay? We have 1 and 2. Oops, different colors. Let's try that. Let's try this again. Let's get some different colors going on here this time. Okay, so there's 1. There's 2. There's 3. To find the zeros, we set each one equal to 0. So yellow, x equals 0. Oh, look, that one's already done. If x minus 3 equaled 0, then wouldn't that mean that x would equal positive 3? We solve. And then the last one, if x plus 5 equaled 0, then wouldn't x have to be negative 5? Okay, so here's what you do with that. Without even using a calculator, I know there's a 0 here at 0, and there's one at positive 3 right there, and there's one at negative 5 right there. At this point, this is when you bring the graphing calculator in, right? So go ahead and type in that top function right there into your graphing calculator. So x, parenthesis, x minus 3, parenthesis, start another parenthesis, then we need x plus 5. Let's hit graph. Now keep this in mind, ladies and gentlemen. See that top tick mark right there? That's 10. Look at your graph. See that? I can't tell you how much or how often I see students look at that graph and see that top tick mark's 10 and completely ignore it. That right there's 40, and then they're just going, whee, gone, and then I guess it comes back. They're just looking at the picture and just trying to hand sketch that graph. That is awful, awful, awful work. You never want to do that. What should you do instead? You got it. We have to go to the table of values and plot those. So the table of values, once again, let's look for that leftmost 0. Go back to the graph. Where was it again? Hey, there's a negative 0 of some sort. So let's go back and hunt for it. Negative, 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 negative. Hey, there it is. Okay, so we need to plot all those between negative 5 and all of those values going all the way up to that positive 0 of 3 right there, right? All the points from negative 5 to 3. So I've taken some screenshots of those, and let's go ahead and use that graph and the graphing calculator's table to plot those points. Hey, negative 5, 0, check, already did it. Negative 4, positive 28 would put you, what, right about here, wouldn't it? Negative 3 and 36 put you about right there. Negative 2, 30, feel pretty confident that it's right there. Negative 1, and then what, 16? Put you about right there. See how we've already graphed 0, 0? And now I need 1 and negative 12. Check. 2, negative 14. Check. And then 3, 0. Because of end behavior, look at all these guys. See how they just keep on getting larger and larger and larger? They're going to because of the end behavior. So now we will have a nice looking graph that we can sketch in. Through the magic of editing, I'm going to skip over the 27 times that I tried to make that curve look somewhat decent. Okay, so there's the front side of that note sheet. Let's look at the next video for the back side.